Good afternoon, everyone. My name is Jalian from Meta, along with my colleague Jimmy. Today, we're going to give you a brief introduction on Nimble at Meta that we recently open sourced as a new file format for large data sets. So during this talk, we're going to go through a couple of sections. So firstly, we're going to go to tell why we need a new file format, and then a brief introduction to Nimble's layout. And then Jimmy's going to cover some advantages that Nimble has over other formats and some technical deep dives into Nimble's bulk and selective readers. And then some brief introduction about the current and future works that we are doing around Meta, around Nimble at Meta. And then we're going to conclude our session with the takeaway section. And of course, last a Q&A session. So why do we need a new file format? So at Meta, ML training is a very large power consumer, if not the largest. And what we've observing is that it's keep growing significantly. And among the training footprint, 30% of the training time are spent on reading the data. And during the talk and discussions with our ML engineers at Meta, we realized that most of our ML training tables are having a very common pattern. So they normally have a super wide or a couple of super wide map columns that contains thousands of features. And when fed into the training fleet, only a small set of features are accessed. And that's what we call a feature projection. So we're thinking, because we've encountered some problems of like improving the existing format. So we're thinking, what if we can have a new format that can make reading data way more faster and more efficient, that can save us tons of money? So on the layout section, I'm going to just introduce a little bit about a generic columnar format first that both applies to the previous Parquet and ORC format that we're currently using at Meta, and also Nimble format. So normally for a columnar format, you shard the entire table into multiple sections or shards that in Dwarf or ORC and Nimble, we call it stripes. So they're essentially row groups, and in Parquet, it's called row group. It's actually called row group. And inside of each stripe, each column is represented with multiple streams. Each stream is just a contiguous run of addresses that we put data together. We put the column data together. So for example, for user ID column, which is an integer column, we have two streams to represent. The first stream is null stream that represents whether or not this particular cell is a null value. And the second stream is the actual data stream. And in the feature column, since this feature is a flat map, which essentially means that each feature inside of this feature map is logically a column and is represented by multiple streams as well. So inside of the red box, right, we can have thousands of streams. Now, if we want to access a stream, how do we locate that stream, right? We have footer informations to help us do that in the current ORC format or ORC format. So the stripe footer is located at end of each stripe, and it contains the location information of each of the data streams, as well as the encoding information of the data streams. So in order to access, for example, if we're doing a feature projection, that means we're only trying to access a single feature out of thousands of features. Right? We need to know the exact location of that data stream's location from the stripe footer. Right? So we deserialize the proto, a stripe footer is represented using protobuf in ORC. So we deserialize the footer and then get that particular stream's location, and then we're able to access that data stream. But since stripe footer is scattered across the file, each stripe has a stripe footer at the end of the stripe. We also need to know the location of the stripe footer. And we can get the location of the stripe footer by looking at the file footer, which is located at the end of the file. And then by looking at the location of the stripe footer, we're able to locate the stripe footer. And then in turn, we're able to locate the data stream that we're interested in. Now, Now, in Nimble format, there is a couple of new things. So encoding metadata is part of the stream. So remember that in the previous file format that we're covering, encoding metadata is inside of stripe footers. But now we've offloaded the encoding metadata into the stream itself. It opens up opportunities for us to reduce the overhead of reading other non-interesting streams encoding metadata. Right? We're only going to be reading our stream of interests encoding metadata. And then it also opens up opportunities for one of the key features that Nimble has, which is nested encodings, which we'll be covering in the next slide. And as you may notice that there's no stripe footers anymore in each of the stripe. And this is because after offloading the metadata, the encoding metadata into the data streams, the stripe footer becomes very light. It essentially only contains the location of the data streams. And it's light enough for us to just push down the stripe footers all the way down to file footer. Nulls are just another encoding. Remember in the previous section, we were giving an example of a user ID representation of multiple data streams. The first data stream is a null data stream, like is null data stream, which represents whether or not this cell is null. So now, since nulls are just another encoding, null's representation is inside of the same stream itself, and that reduces the need of maintaining an extra stream. And fewer streams means less metadata, right? And of course, nulls are optional. If this column is not nullable, we simply just don't apply an additional null encoding on top of the encoding. Another key difference is the transition from protobuffer thrift from previous format, dwarf or Parquet format, to the flat buffers from Google. So what flat buffers can offer is direct access without parsing. So flat buffer is having this in-memory-like layout so that after loading it, you don't have to deserialize it. You directly access the element you want to access. Imagine, let's do a quick comparison of how we access a particular data stream of the old format and the new format. So in ORC format, you issue an IO, right, to retrieve the file footer, and then you deserialize the entire file footer, and then you get the location of the stripe footer, and then you issue another IO to retrieve the stripe footer, and then you need to deserialize the entire stripe footer in order to access just that particular data stream that you're interested in. So that's 3 IOs, right? 3 IOs because last IO is the IO that you're reading the actual data stream. 3 IOs plus 2 full deserializations. What about Nimble? You issue an IO to retrieve the file footer, right? Because you don't need to parse it. You just read the exact location. You just read the exact location of the data stream you're interested in. Get the location, issue another IO, and you get the data. So that's 2 IOs, no serialization, no deserializations. Encodings. One of the key offering of Nimble is nested encodings. On the right, it lays out the layout of a stream. Inside of a stream, we have an encoding header at the front, and then after encoding header, we have the encoding data. What's different is inside of the encoding data, you can have another encoding representing a chunk of data inside of the outer encoding. And inside of the sub-encoding, you can have another sub-encoding too. It's a tree that you can build based on your data pattern to maximize the performance of the data of interest. For example, a dictionary encoding could be the outer encoding, right? Inside of a dictionary encoding, you have a data set that represents the indexes of each rows, pointing to what values of the dictionary. And then you have another data set that represents the limited amount of values inside of the dictionary. So for example, your indexes could be 000, 111, 224. And then it makes sense to further encode the indexes datasets with RLE, round length encoding. This is the list of encodings that we currently support, and we're planning more. One of the most important things about the encoding is that it is format decoupled, right? And then you can write your custom encoding according to the API and then plugged in to the framework, and you're working seamlessly with other encodings. So now I'll pass over to Jimmy.
Yeah, so now I'm going to introduce some advantages that comparing in our practice, comparing Nimble to our older door format. So first, it's as Jialiang has mentioned, that more efficient. We have more like efficient encoding with this net and flexibility with this nested encoding like capability. So that enable us to compress data furthermore. And we can try and different algorithms, new algorithms like ALP, streaming variant, and FSST, doing all these experiments and try it. These are also pluggable, so you can try it. If it's not useful, then just ditch it. So that and at the end of the day, if you find something useful, then you can keep it. Otherwise, just try it. These can lower the cost of experiment and push the compression ratio to furthermore a limit. The second thing is that in addition to these encodings, we can also apply like a chunk level compression. Like Jialiang mentioned that in a stream we can have like encoding, but there's also can be multiple chunks. Then inside the one stream, that each chunk can have a different encoding. So like say row like 1 to row 10,000 is one kind of encoding, and row 10,000 1 to like 20,000 another encoding. And each one of these can be applied with a compression, like a special compression algorithm that the user choose that can and it's pluggable, so that it can be compressed. And at this level, you have the type information with the data. So some like a type aware compression algorithm could be applied. That we inside the meta we achieved quite a good result with these things. And these two things combined together, that gives about like 10% storage reduction overall. So that's just for the data itself. So it's with less data stored, and that means less data transferred when we read it, and that improved from the point of view of computing engine, that also like increase our efficiency and wall time as well. So another aspect for the advantage of Nimble, so it's on the metadata aspect that Jialiang also mentioned, that we use flat buffers, so that's zero copy when we're reading it, and no overhead at all, no decompression, no CPU, not even like memory, like you don't need to do a copy of memory for the decoded data. So that's a very, very low footprint when we read metadata. Before we was like for the flat map format that Pedro also mentioned before in his talk, that we have like tens of thousands of fields, and each field has metadata, so that will incur a lot of like overhead when we're trying to read them. These are all eliminated inside the Nimble. Also, the metadata now is not just the field metadata, but now they are in one place. So as Jialiang just mentioned, we just need to issue one IO, and then we can get all the metadata for one file, and no need to issue a second IO for a separate like stripe level metadata. So just that become very IO efficient. And furthermore, that furthermore, that there is more advantage if we want to read it from GPU, because in GPU reading, that the metadata is supposed to be read from CPU, so that but the metadata if we have to read the stripe level metadata inside the GPU, then that's too IO that we cannot schedule it together. So that will have a more advantage when we hook the thing with the accelerator. So that's another advantage that it's not obvious now, but will be useful. And another advantage that inside the design of Nimble, that we have fewer string for each field, so we don't have null string. So that means before they'll have both null string and value string, so that we need to issue separate IO for them. Sometimes it can be usually stored together, but sometimes it's not. So that's 2 IO. Actually, it could be 2 IO. But in Nimble, it's guaranteed to be like a one contiguous region. So it's just a 1 IO. So add these together, just from the reading of metadata point of view, that we can reduce from one experiment to reading a single column. It requires 170 millisecond just the parsing metadata in Dwarf. Whereas if we convert that file into Nimble and read it, it just took like 1.3 milliseconds. It's more than 100 times faster when we're reading metadata. So next slide. So another thing in addition to the nested encoding is at the leaf level. So these are only applied to primitive types, including string, of course. But it's not applied to array and map. But these things also worse compression that sometimes. So in addition to the nested encoding, we also add special types for array and map that allows us to simulate run length encoding for these types. So basically, it's adding a stream of offset and check if the offset and size are identical to the previous one in the reader. And if they are the same, then we use a dictionary to wrap around the result, so that these things we don't need to like make a copy of the whole array or map. That thing also saves a lot of space in addition to the nested encoding and the compression that we got. So next. And now I'm going to have some like very brief introduction about how the reader are implemented in the Nimble reader are implemented. We have two set of reader. The first reader is a bulk reader. That one is already out there in the GitHub, Nimble GitHub repo. It's fully open sourced, and it's very clean designed and easy to read, and it's very efficient. So how much efficient it's actually now when we compare it with Dwarf version with Dwarf version with no select lower filtering rate, means that there's a lot of things are selected and nothing is filtered out. This thing is already beating Dwarf reader. And the C++ version is fully sourced in Nimble in the GitHub repository. Java, we also have a Java reader, but that's open source of that version is planned, but it's not open sourced yet. We need to plan that yet. And the Java version, we already did the experiment during our migration of tables. That's already like better than the select. Even in the selective, consider all the cases, including selectivity and selective cases and non-selective cases. When we already had achieved like overall performance that better than the Dwarf reader in Java version already. There is some regression on selectivity reader, but we will make it up with the next selective reader. And the bulk reader, the structure of a bulk reader is quite simple. So basically there are two parts. One is the tablet reader. Tablet reader is the common in selective and in bulk. These are the functionality of that part is to read the metadata, which is basically a parser of the flat buffer data, but that's very lightweight. And the structure of each stream inside each stripe is exactly the same. All the offsets are the same. So you just need to parse it once, and then you apply it to all the stripes. And the actual data is read from the field reader. And each field reader is a tree, so that you have a field reader under the field reader for nested types. And then inside the field reader, you have decoders to decode the actual data. And the decoders are nested so that you can decode the data like recursively. So next, And now we are working on a new selective reader for Nimble in C++, and because that we saw that there is some minor regression with selective comparing to Java selective reader when we roll out the bulk Java reader in Nimble. So that we are working on a selective reader, so that's going to be integrated with Presto very soon. And the selective reader is reusing the Vlogs selective reader framework, so that all these like format agnostics optimization, we will get it for free. For example, on IO side, we can get the cache and the coalescing more efficient IO for free, so that these IOs are like optimized when connected to aggregated storage. And there are also these optimizations that format agnostic, like mutation and things like that. We also get them for free. And the structure of the selective row reader is a little bit more complex than the bulk reader, because in addition to the metadata, we also need to have this the schedule of IOs, this layer of scheduling IOs and the caching, so that the IO layer can be optimized. So we wrap the tablet reader along with a stripe stream, like a scheduler, inside a reader base. And on the data plane, we also have this selective column reader, which is sort of one-to-one mapping to a field reader, but with the capacity of reading one batch using according to row numbers to select and filter as well, so that we read only like a subset of rows that we need.
Cool. Thanks, Jimmy. So I'm going to give a brief updates on what's currently happening at Meta about Nimble. So we already convert some training tables and put them into production. And the consumer being the ML training data preprocessing that is using Nimble C++ batch reader. And then we'll also have Presto in production, and it's leveraging the Nimble format by using the Java batch reader for consuming those tables for batch or interactive processing. And we've already realized savings, from those ML training capacity and time due to the advantages that Jimmy just covered, essentially better encoding and better metadata handling. And of course, since it's a relatively new format, we also built a comprehensive testing environment to give us better confidence on the new file format. So we've tailored Presto Verifier as well as Presto Query Bank to serve our needs. And in the future, we're going to be continuing migrating ML training tables. And in addition to ML training tables, we're going to also expand our Nimble coverage to more general purpose tables inside of our warehouse, such as general batch or even analytical workloads. That's still yet to be evaluated. And of course, we're going to continue experimenting and analyzing of more types of encodings, thanks to its super flexible, pluggable encoding framework. And further down the road, we're going to improve Nimble for data processing on GPU. On the Presto side, we're going to be completing the writing support on Prestissimo, which is Presto C++, sometime in the future. And also, we are currently having Nimble selective reader under construction for both Presto and Prestissimo. And hopefully it will be in production and serve better performance for our even for our analytical workloads, or for the workloads that has higher selective rate. So the takeaway for today's talk is Nimble is open sourced and integrated in Prestissimo stack. And here's the link for Nimble. Please go and take a look. And Nimble is more efficient in terms of layout and for patterns common in ML workloads. Nimble is more flexible in terms of encodings, right? And because of that, we realize the storage and read performance savings. Finally, but not least, Nimble is very GPU friendly on decoding. Thanks, everyone. This is our talk today, and any questions so far?